So welcome everyone to this open problem session. It's 5:30, so we're going to try to start on time. I know everyone's very hungry, very eager to get started with the discussion of the problems and also get some dinner soon. So I want to thank you on behalf of my co-chairs, Ashley, Animesh, and myself for coming here and for joining us. We know it's been a long day. So the goal of this session is really to help spark discussion, right? So we've been seeing a lot of sort of challenges over the day and a lot of sort of different solutions. And we wanted to take a little bit of time to just highlight some of the open problems that we see still facing robotics. And it'll hopefully sort of spark some inspiration and discussion amongst the attendants. So obviously, you know, we're going to have a little bit of time to discuss during the session, but we're hoping that, you know, this our problems that we're presenting are going to be some food for thought as you go out for dinner as well. And so I hope you enjoy. I'm going to be presenting the first open problem, and then Animesh is going to be presenting the second one. And the problem I'm going to be presenting is modeling the preconditions of skills during learning. So in the future, we want robots to operate in open world environments. They're going to be coming across new objects. They're going to be performing new tasks. And ultimately, they're going to be learning skills over a very long period of time. And, you know, they're going to be working in different domains. So kitchen robotics, hospitals, safety and recovery, agriculture, lots of different domains. And I think that robots should know what they are capable of doing. And I just want to see a quick show of hands. So robots working in the open world, who would agree that they should generally know what they're capable of doing in those environments? All right, good. So I've settled you on the main premise. Great. So whenever I think about robot capabilities, the first thing that jumps to my mind is actually preconditions. So preconditions, you've probably heard about them in terms of sort of task planning, initiation sets for options, the can and say can. But the key idea is really that a robot can sort of model in which state is actually going to achieve a certain goal. So we're going to assume we have some parameterized skill pi. We're going to have a goal, which if we achieve it, we get a 1. If we don't get it, we get a 0. And the goal of the preconditions is to take in different task states and tell us what is the probability that we're actually going to achieve the goal of this skill, right? And so before we talk about sort of modeling it, I like to sort of think about it sort of in this graph shown here, which we can think of sort of the ground truth preconditions. All right, so we have along the x-axis the task status, so the state that we're putting in, and for every single possible state, we're going to get a value between 0 and 1, indicating what is the probability of actually being able to succeed, right? And this is our ground truth state. So in this case, you know, this is the actual success likelihood given that state. Now, just as an example, we can consider grasping. So for example, here, one point along this axis might represent grasping a cup. In that case, we have a very high success probability. Most robotics researchers are going to include some cups in their data set. We might also have a knife, which may be a little bit more difficult to pick up. We also have a shovel down here. So shovel might require, you know, something a little bit more knowledge about the object. And so, or maybe even by manual grasping. So that's maybe a little bit more difficult. So we're going to have a lower sort of value there. What about this needle? Is this an easy object to grasp for the robot or difficult? Difficult. All right, great. So the other part of so it's important to note that obviously there's going to be a lot of different dimensions for this task state. So this sort of horizontal axis where we have is doing some very heavy lifting. It's going to capture the size, the shape of the objects, the materials, constraints, other objects. We're just going to sort of treat it as one axis and sort of think about it in the abstract. Now, the other aspect that we should be thinking about is the actual task distribution, right? What are the situations that the robot is going to be asked to actually perform this task? What are the sort of the distribution over that state? And if we combine these two, we get something that we're all very familiar with, the success rate, right? So if we integrate out the state over these two distributions, so one conditional and one marginal, we're going to get the actual success rate in this kind of a task distribution. Now, if we have, for example, a much narrower task distribution, right? So this is what we might see in a factory setting. So we're not going to see a lot of variations. In that case, you know, we don't also have to have a very versatile skill. We can have something that's much more sort of focused. right? And so anywhere sort of within these two sort of vertical bars, that's going to be sort of suitable for actually executing this task. Now, in practice, it's not going to be quite that easy. So, we're going to have a distribution that's maybe a little more complicated than everything being in, situations where it's perfect, which is really one of the challenges of the open world. But if we do have objects or tasks within that sort of narrow band, then, that's great. That means we can actually perform those autonomously. But what about if we're outside of that region? What could we do then? Well, one thing we could do is we could try to avoid it, right? We could try to replan, sort of say we can't do this, but maybe, we need a different metallic object. Maybe that'll work for the task. So maybe we can kind of get around it. Or we can actually ask a human, right? So a human could potentially come in and help the robot in cases where it knows that it's not actually capable of performing the task. Now, obviously, that was sort of the ground truth preconditions. That's sort of the ideal. So if we knew that, that would be great. But in practice, we're obviously going to have a model that kind of tries to capture this as accurately as possible, shown here in orange. Right. And as we sort of, use this model, we can sort of do the same kind of thinking or reasoning where we sort of say, these are situations where we can use this skill and it's going to lead to the successful outcome, or we can execute it and it's going to, fail. So we should probably ask for help or try to replan. The errors that we sort of get in here are the ones of overestimating and underestimating. So if we overestimate, we're going to get sort of erroneous executions where as we sort of try this task, it's going to fail in the real world, which we obviously don't want to have. What about underestimating? What happens if we underestimate our preconditions? Any ideas? Shout it out. You're going to ask for help when you don't need it. Exactly. You're going to avoid using a skill when you could, and you're going to sort of ask for help when you don't need it. So the more accurately we can sort of model our ground truth preconditions, the better. Now, the nice thing about precondition learning is that it can be learned in a self-supervised manner. So often what we do is we give the robot some kind of an indicator of the goal. We give it a learned skill. And we just have the robot execute it in lots of different situations, observe what the resulting goal is. And from that, we can learn this probabilistic model or classifier effectively, which is going to capture our preconditions for how well we can perform the task in different situations. Now, in many cases, when we're sort of learning these preconditions, we have a fixed skill, right? And so that's kind of the key challenge I want to sort of, propose is that this becomes a lot more difficult when we actually have a skill that's being learned. So in that case, we might have our original old preconditions, but as the robot is effectively learning, it's going to get better and better at performing this task in various different situations, right? And so we're going to get something that looks maybe like the pink line here, which is definitely higher in certain regions, but it's also sort of lower in other ones as we sort of observe some forgetting. And so what we want to do is we want to be able to sort of keep up with that kind of precondition model. And this is specifically a problem in open world environments where we might also have the state distribution shifting, right? So it might be that, you're helping out at a home, maybe, starting off as a child, there's some playing with blocks, they grow up, they're no longer playing with blocks, and at some point they're going to have their own kids and you're going to return to blocks again. And, will the robot still be able to perform the task that it did when you were younger? And so the question is, how do we efficiently model preconditions over time? And we do have some additional information. So every time that we're executing now a skill, we also have different parameters that we might need to consider. So, this is sort of the key change between our samples now that we need to consider. And we also have the individual trajectories being generated from, those skill executions. So that's sort of the key problem I want to highlight. Obviously, there's a lot of sort of related problems that you can think about. It's kind of shown up here. So for example, one I'd love to ask for everyone is, what priors would be useful for incorporating into our precondition models, for example? Any thoughts? Okay. All right. So this is just a nice list of questions, and I'm going to be a little bit afterwards here, but I suggest that we're going to switch over to the next presentation and have Animesh present his problem. All right, thank you.
Oh, thank you, Oliver, and thanks a lot, everyone, for having been at CoRL. I'm missing out, clearly. I hope you have had a wonderful event so far, and it has been wonderful working with the organizers doing this. Oliver presented today the idea of preconditions, which is basically given a particular setup. What sort of abilities does the system have given a group? And I thought perhaps it would be a good idea to discuss slightly more broader problem, less technical, but equally important. Where do these goals come from? A lot of the times when we are doing decision making, we assume that the goal is given and measurable. Think of simple things like maybe opening a door or opening a jar. Could we define that cleanly? What does it mean to open a door? Is it always this particular door, any random door? What about opening a jar? Or maybe if you're not given the concept of an object, but you're given some perceptual input. So let's say an image or RGBT input, and you're given an action open. How do we process that? Currently, when we think about these problems, we might use either of these solutions. We might build a learned classifier, which tells us when the task is completed. Or under the hood, we might use some privileged state information to evaluate if the task is completed, and then also compute some sort of reward function or cost function. Often this cost function can be computed as a function of state. And if we do it very simply, we figure out, as many students might already know from their empirical adventures, that simple reward functions which are sparse are really kind of hard to work with. And this is where I would say engineering or reward tuning starts. First of all, we might want to make this slightly more amenable to optimization. So we might make this dense, perhaps even continuous. And often if you look at the reward functions that we use currently, at least in the reinforcement learning literature, it might look something like this, where you have different reward components that are put together in some, let's say, additive fashion. These reward components often can be simple things like distance to goal, energy, but often can also be very non-intuitive. It has been surprising when I've looked through the papers, even published this year, how different things people have come up with. And each of them come with their own knobs. For example, how to mix them, it's not always clear. It's a lot of trial and error just to figure out what would work. And a lot of engineering is going on. And even then, actually, one of the things we realize is maybe we need to actually change this mixing over time. So for example, some reward component is active only for the first part of the task, and then it goes away. So essentially, we are coaxing the system, the optimization model, into a solution that we want. Now, this idea can give us, let's say, a solution for a particular problem that we have, but we really want to do many tasks, as Oli pointed out earlier, that we really want to be able to do not just one, but many tasks. And I think a good example or thinking exercise is, well, food for thought using food is, what would be good reward models for tasks that go in simple activities such as food preparation, chopping carrots, potatoes, or breaking eggs, mixing eggs, cooking eggs. These are really very hard problems to even define in measurable reward functions, and even hard to create, let's say, learnable reward functions for, or usable reward functions. So one of the solutions, or one of the ideas, I would argue, has been that what if we could separate the what and the how? So far, these reward models have been tuned particularly for the solution we are interested in, but it might be interesting to see if we can specify tasks that are independent of the morphology that we are going to use. So think of it like this, that To open a door, you might provide some instruction to say, take an object, open fridge, put an object in the fridge, right? This is basically thinking of moving objects in worlds where there is no particular actor person. And this allows us to capture effect of actions. And in one setting, you can really think of this as you are doing a reference or a goal generation that can be passed on to some agent-centric planner, which can use whether learning or a model-based controller to come up with a solution for this problem. So this is what I would recommend saying what and how. So the what problem is basically saying, given some sort of description of the task, come up with a representation of the goal in some reference frame. And that is what brings us to questions. When we say reference frames, what reference frame should we be using? Should we be using object reference frame, the egocentric robot reference frame, or some sort of world coordinate system? And similarly, when we think of how, does the task definition depend on the morphology of the robot? For example, is the notion or the concept of opening a door dependent on the fact that the agent is a human, a left-handed human, a right-handed human, or a robot, or maybe a baby? And if yes, could we define it at least over classes of morphologies? So this is one intuition to think about. The other one is the separation of what and how allows us to think about how we can use large-scale pre-training, particularly on the what component. So I don't need to preach to this audience that large-scale pre-trained models have well grown, both in size and in popularity. They have also made a lot of advances in different kinds of subfields, from text to images, text to videos, text to image, 3D as well. But I think jumping to the point is, while we have seen a lot of interesting advances and also interest in the community using these models, they're not perfect. They're not perfect in the sense that while these systems can capture, even the multimodal systems can capture notions of what I would call nouns and adjectives, something like a person wearing a black t-shirt, crossed arms. But they're kind of bad at verbs and adverbs. Open dishwasher, or show me the process of opening a dishwasher, is actually much worse in these models. Perhaps it's because of the data. Perhaps it's because of how these things are trained. And then there's problem of grounding. Right? Make eggs may have many different types. Some of them may not always be simply explainable. There is also a problem of grounding of attributes beyond just the ones that we see easily. So the systems that we have already can attempt things like bring me the red napkin from the kitchen, but problems like I am sitting on a table and I want a fork, but I don't actually say clean fork. I say, can you get me a fork? Should you get me a fork from the sink, which is readily available, or should you get me a clean fork from probably inside the drawer? So context is hard. That sort of grounding is much harder to do. Similarly, these models which have been doing planning are not always closed loop. If you say, make me an omelet, and what happens if you don't actually have eggs in the house? So bringing back this to questions, think in addition to the questions that we already posed, there are two more questions. If we want to do large-scale pre-training for robotics, what sort of data is needed, particularly for this sort of grounding? Is it language only? Some have argued that language, by the nature of its generation, captures implicit grounding. It could also be images, videos, 3D, perhaps even other modalities like touch. But scaling these things has not been very easy. So that is a question I believe lies in our docket. Similarly, grounding of multimodal spatiotemporal concepts is something that roboticists in general will care about because of the embodied nature of our problems, which may not be the primary application in generative AI. So this is an application of these large-scale generative model that is slightly different from the popular use cases. And how would these models need to be adapted? I would not stand between you and dinner anymore, but thank you for your time, and hope you have a wonderful discussion.
All righty. Thank you, everyone. So I think in the interest of time, we're Well, we can take some questions. Okay. So we can take some questions now.
Could we use value functions for precondition classifiers? And does it make the problem easier or harder, or is there any difference between the two?
So there is a sort of the situation where you effectively say that you have a reward of 1 at the end and 0 everywhere else, in which case you do get something very similar to kind of a precondition. And with your value, assuming you don't have a discount, I would say that, should I stop sharing? Oh, no, you can keep sharing, Unmesh. I would say that, one important thing is that you do need to make sure that you get a good value function. So often when we think about values, it's all about relative value functions. And, if one is bigger than the other, that's great. But in this case, we really want to make sure that the value is actually very close to what it should ultimately be. But I agree that that is another way to think about preconditions.
Thank you.
Hey, Animesh, this is maybe a question / open problem. So when you talk about task specification, do you also consider specification of the strategy used to solve that task? So for example, as we are getting into like more learning from humans, more learning from language models, something that's coming up is the representation used, or the representation of the strategy used to solve that task, and whether that's in the form of a sequence of steps from a language model or some other abstract representation. Is that like something you think is included in this task specification definition?
That's actually a wonderful question. I don't have a solution or a definitive answer. However, I believe, this is my hypothesis, the specification of the task should be independent of the actor. For example, opening a water bottle does not really depend on the fact that if you're left-handed, right-handed, or where the bottle is stored. So there is a notion of invariance for the successful execution of a task. What might happen is, dependent on the affordances or the abilities of a particular morphology or a particular agent, some task specifications might not be achievable. So that may happen. However, I do believe task specification can in principle be independent. Now, when you are interested, not you per se, when we are interested in going from data, let's say human collected data, to a morphology of, let's say a 2-finger robot gripper, the same sequence of steps may not work out because of the change in morphology. So we need to find the parts that are invariant and that may only exist for a particular morphological class.
Yeah, hello. So I have like a new problem to kind of discuss, which is like a lot of work is going toward these large models, right? We're kind of accumulating more and more data. We're training these larger and larger models. And especially if you have to reach the same level of generalization as language models, we have to really train very large models, like of the order of maybe billions of parameters, if not more. So one question is like, okay, how do you make sure that we can do good robot inference and in like good time? That I feel is an open problem. And secondly, to continue on that, how do you then take that and then still continue doing some fine tuning or some sort of on the job learning, which kind of goes hand in hand with like, okay, how can you do inference with those models and keep learning? So I feel this as a very important problem, because the field is moving towards these large models with lots of data.
There's a question up here as well.
So I had 2 comments. One, I wanted to respond to Animesh. I think that it's probably, if we think about sort of the classical literature going back to 50s and 60s, there was essentially the view which came from the symbolic AI community, which is going back to GPS of Newell and Simon, and then the STRIPS work, which always thought in terms of goals and sub-goals, right? And in fact, oftentimes that's what we are trying to do. We have a certain goal, then we realize that it's too hard to solve the problem to the goal directly, and then we define sub-goals and so on. Then there is this style of reward and reinforcement learning, which I would regard as basically converting the idea of utility, which is in economics, and a sequential version of that problem and putting it here. And the arrogance of the reward people, and it's in chapter 2 of Sutton and Bartow, is that reward is sufficient, right? And it's essentially the basic thesis is whenever you define a goal, you can convert it to a reward, because you can say a reward equals 1 when a goal is achieved. And in a certain trivial sense, that is true, but it is actually philosophically quite wrong. And I think that's where all these problems are coming from. What we are doing is there are settings where we want to operate with various kinds of sub-goals, and we try to sneak them in by the back door by adding various terms in the reward function. And I think that we should just be more honest about it and not try to sneak it in this way. Now, the question is, does this mean that we have to go back to classic symbolic logic and so on? I don't think so, because these intermediate sub-goals, we could define them in a continuous way, right? Just like a word is in language, it's considered a symbol, but nowadays a word is really a 300-dimensional vector, okay, in some space. So I think that if we think of goals as embedding vectors and sub-goals as embedding vectors, we might have a way of proceeding which delivers us from this god of rewards are the only way we know how to specify tasks. I think it's just not natural. The econ people have moved out of it, right? The old style econ was, yes, it's always, we are all humans, utility maximizers. All of behavioral economics, Tversky and Kahneman, it's all based on the realization that real humans don't behave like that. So,
thanks a lot, Jitendra. I think this was a very useful insight. Absolutely. Not everything is Markovian. A lot of people are looking into non-Markovian rewards, but we don't have, let's say, algorithmic infrastructure that is equally developed for that framework. But I think this would be a perfectly green space for new students to look into.
Yeah, actually piggybacking on Jitendra's point, because we're at CoRL and we're seeing a lot of seem to real, and also because a major application of robotics is going to be amplifying people, assisting people. One of the things that I think I haven't seen in almost any singular like simulation result today is simulation of people. So, you know, piggybacking on this, I think one of the challenges that we have to wonder is if we're going to design people that interact, robots that interact with people, do we need to have really good models of people in simulation, which we do have when it comes to geometry and appearance. I would argue we don't have when it comes to motivation, intentions, and you know, maybe some of these economic factors that Jitendra was talking about, or you know, is it out of the realm of simulation? So I think that's an interesting question for the CoRL audience, people in simulation. I think we haven't seen too much of it, at least this week so far.
Yeah, absolutely. So I mean, yeah, I think also just modeling the physicality of humans and then the properties. Obviously, there's a lot of challenges there. I think that's a great point. I guess I was mention one thing about sub-goals for manipulation. I feel like manipulation does have a lot of structure in terms of also modes. And so for me, modes are a very common sort of sub-goal because it's all about the fact that there is something that you can test afterwards, right? It's something that there's a change, a jump in the dynamics, and therefore it's not just about reaching a certain state, but it's a state in which your effects of your actions are changing. And so there's something that can be tested and verified autonomously. All right,
There's a comment online. So I'll throw an out or two out real quickly. Since it seems another thing that seems so big this year in particular is the use of latent vectors and autoencoders to find these vectors. I wonder, I haven't seen too much talking about how to optimize the size of these vectors, because obviously if they're too large, you don't get the effective compression. If they're too small, there seems that there's going to be some kind of aliasing that's going to happen, and that is that you've sort of over narrowed the specification. So I'm curious if there's ways to tune that very efficiently. And the second problem is around the analogy to adversarial images. I think it would be very interesting for us to look for adversarial cases in robotics where, for example, objects that are difficult to grasp or scenarios that are, let's say, terrain that's very difficult to cross, right? Can we construct that systematically in the same way that it's done in computer vision to find those cases? Because I think that emphasis on the failure modes is something that would be very helpful in our field and give us a perspective. And so often we show the success rates and maybe a few failures, on the side, but systematically showing that there is possible to generate failure modes, I think would be really interesting, and I haven't seen that yet.
There is a comment online from Haruki Nishimura. I'll just read it. I wanted to throw a general question on safety aspects that might be overlooked. How would safety come into play when we think of what and how in task specification and execution? How should we even define a suitable notion of safety for embodied agents in order to make sure we can deploy those robots with confidence in real life situations?
I suppose there is no right answer here, but I would assume that the first approach might look at the task specification first as a separate problem, and then the solution, whether it's learning based or optimization based, to include safety constraints in that setup, to find solutions that are bounded under certain notions of safety.
So if there's no last question or problems that people want to raise, it is already past 6 o'clock. So I just want to thank everyone for joining for this session. Thank you and I hope you continue a lot of lively discussions after this. Thank you.
Thank you.